I'm actually up over here, but down here we have a couple islands. Seattle is over there. This is what we call the Olympic Peninsula. And so one of the things we can map is how the currents come through what we call the Strait of Juan de Fuca, this really nice bar of water that comes between Canada and the U.S. over in Washington State, and then flows down into the Puget Sound. Tidal currents are really important for a couple of reasons. People like me care about them because they're going to impact where we want to surf, and where we go out, and where we come back in. They're also really important because Seattle operates a ferry system that goes from Seattle across the peninsula. So there's a couple different ferries that run from here over and from here over. And so one of the things you want to do is you want to know exactly where water is flowing and how, so that when you plan out the route, you can maximize your efficiency by going with the vector, minimizing the force required. And so this is just one example. Here you can see one that's kind of in 3 dimensions. You can see the fact that as you drop down in Z, that is, as you drop down in water depth, the direction that the water's headed actually kind of shifts, which is kind of interesting. You can see through those stacks right there. And here we have the 2-dimensional vector fields. And you can see coming in here, the vectors are much longer, so the magnitude's bigger, which means what about the water currents, do you think? The water's flowing faster, it's got a stronger current. And then once you get in, this is water flowing in from the ocean. Once you get in, the water speed dies out, right? And we can tell that by the vectors getting smaller, both in thickness and in length. This is one application for vector fields. I kind of want to show you. It's kind of interesting, at least to me. So that being said, we're going to go ahead and we're going to pick back up, talking about vector fields today. I've already saw a really awesomely drawn map. And let's go ahead and talk about some examples. So once again, getting into vector fields. One of the examples we're going to be looking at today is gravity and the force exerted between 2 objects of mass M. And little m. And so what we're going to look at is actually one of the laws of physics you guys have probably already covered. That is, I can write F of F is equal to, and we'll put this right here. Actually, we'll go ahead and we'll start from the beginning. But the magnitude of F is equal to mg over r squared. That is where g is my gravitational constant. And r is my radius between the 2 bodies. If you do not think my g looks enough like a g, there you go. No. Now I write this with the absolute value around it, right here, because what we're talking about here is an absolute value, or the positive, the measure of the magnitude, I guess. And what we want to do is we want to translate this into a function, and so what we can write is f of x, where x is the vector between the 2 bodies. That is, we can write it as a function rather than just our little equation there. Now the important thing here is it's a function of a vector, right? So I'm plugging in an x value. What we want to do is we want to rewrite this somehow. Now what we're going to do is we're going to take one of those objects and we're going to place them at the origin of our graph. Because in reality, whenever we're dealing with physics examples, we probably don't have axes. We can create them artificially. So it's easy for me to be able to take one of those objects and put it right in the center. So what I'm going to do is I'm going to put a little ball right in the center. This will be one of my objects. We'll say this is the object with mass m. And what we're looking at here is how are the forces acting when we look at these 2. Now, to do this, we need to go ahead and we need to look at our function. I'm still going to have m, right? I'm still going to have big M, and I'm still going to have g. But this r squared, I can actually do something with that. That is, if I'm looking at the vector x in between these 2 objects, r measures the distance between those 2 objects, right? What relation do r and x have? If x is vector in between two objects, and r is the distance in between those two objects, what's the relationship between x and r? Well, what can I do with the vector? What do we think? Well, if I have a vector in between, to find that distance, all I do is take the magnitude, right? And so that's exactly right. That is the magnitude of x is equal to r. Now the reason why this is helpful, the reason why this is kind of interesting here, is that means I can get rid of this r on the bottom, right? That is, if r is equal to magnitude of x, then r squared is equal to magnitude of x squared. Now there's one other thing here. When I write f of x, I'm trying to write out a vector field, right? Which means it's not just enough for me to go ahead and get this, because what does that give me? Is that a vector? What is that? Just a number, it's a scalar, right? And f should give me a vector field. So not only should I have that number, but I should also have a direction. So I need to add in a directional component. Well, x is measuring, once again, the vector between the two of them. What I want to do is I want to take that vector and I want to find the direction of it. Well, when I look at the direction, I can look at just x, right? I mean, x has a directional component. But if I put another x in here, x also has a magnitude, right? I don't want to add in another number. I just want the directional component of x. In order to look at that, what we're going to do is we're going to take x and we're going to convert it to a unit vector. The reason why we convert it to a unit vector is to keep the direction but get a magnitude of 1. That means that when we put that x or that whatever value in there, it's not going to play with the number, it's just going to give it a direction to go in. How do I convert something to a unit vector? Let's start to chapter 10. Are we going to divide by the magnitude? What do we think? Well, something's got magnitude 2 and I divide it by 2, what will the new magnitude be? 1, right? So that's exactly right. To convert something to a unit vector, I divide by the magnitude. Okay? So I'll take x and divide it by the magnitude of x. That will give me just a directional component. Now here's the problem, guys. Here's my big question for you. If I've got my object of larger mass in the center and an object of smaller mass out here, where's my gravitational force acting? Out or in? Something big, something small, which one's getting pulled where? It's getting pulled towards the center, right? Which raises the question, what do I have to change about this to make sure that